A black hole is nature's ultimate one-way street. But what if the universe has a cosmic exit door, a place where reality itself flows the opposite way? This is the white hole, a theoretical fountain of matter and energy that could rewrite the rules of physics. By the end, you will understand why this ghostly twin could be the key to the universe's deepest secrets, from the Big Bang to the fate of information itself. We will explore how a simple mathematical flip predicts its existence, and why seeing one would shatter our current cosmic models. What does it mean for our reality if creation can erupt from a single point of infinite density? Symmetry is a silent language spoken by the universe itself. We see it in the perfect reflection of a butterfly's wings, in the opposing poles of a magnet that forever attract and repel. It is a principle that whispers order into chaos, suggesting that for every action, there may be an equal and opposite reaction. So when we look at the most terrifyingly asymmetrical object we know, a black hole, a simple, profound question emerges. What is its opposite? The answer, hidden within the very mathematics that predicted black holes, is the white hole. Think of it as the ultimate cosmic mirror. Where a black hole possesses an event horizon that acts as a point of no return, a one-way street where matter and light can fall in but never escape, a white hole flips the script entirely. Its event horizon is a one-way street going the other way. Nothing, not even light, can cross from the outside in. It is an exit door with no handle on the outside, a theoretical fountain from which reality itself could be pouring out. This isn't just a poetic idea. It emerged directly from Albert Einstein's equations of general relativity. Mathematicians exploring these equations found that if you take the solution for a black hole and simply reverse the direction of time in the mathematics, you get a white hole. It is a perfectly valid, symmetrical solution to the most successful theory of gravity we have. This means the white hole isn't a wild fantasy. It is a ghostly twin predicted by our deepest understanding of space and time. Its existence forces us to ask a startling question. Is the relentless forward march of time we experience merely a local condition, while the mathematics of the cosmos remains perfectly, beautifully reversible? The year was 1916, and the world was at war. Yet in the midst of that conflict, a German physicist named Carl Schwarzschild was performing a different kind of exploration, one that looked not across trenches but into the fabric of the cosmos itself. Stationed on the Russian front, he received a paper detailing Albert Einstein's new theory of gravity, general relativity. With remarkable speed, Schwarzschild did something extraordinary. He found the first exact solution to Einstein's immensely complex field equations. He described with beautiful precision how space and time would curve around a perfectly spherical, non-rotating mass, like a single star sitting alone in the void. This solution, now called the Schwarzschild metric, was a triumph. But within its elegant mathematics lay a hidden strangeness, a set of boundaries where the equations seemed to break down, producing values of infinite density and curvature. At the time, these points were considered mathematical oddities, perhaps artifacts with no real physical meaning. Scientists, including Einstein, largely dismissed them as impossible. They did not yet have a name for what those boundaries described. We now call one of them the event horizon of a black hole, but the mathematics held a deeper, more symmetrical secret. When physicists later mapped the full implications of Schwarzschild's solution, they didn't just find one mysterious region, they found two. By extending the geometry to its complete logical conclusion, they discovered the solution naturally described a pair of connected but separate realms. On one side, the now familiar black hole, a region from which nothing can return. On the other, its perfect inverse, a region into which nothing can enter, a white hole. They are two sides of the same mathematical coin, revealed not by inventing new physics, but by simply following the equations where they led. To visualize this, physicists use a tool called a maximally extended spacetime diagram. It is a map of all possible paths through this curved geometry. In this map, the black hole and the white hole are distinct regions, but they are connected by a theoretical tunnel, an Einstein-Rosen Bridge, often imagined as a wormhole. This bridge is not a stable passage you could travel through. It is a fleeting mathematical link. The white hole in this picture is not an optional add-on. It is an inevitable part of the geometry that emerges from Einstein's own rules. This means the concept was not dreamed up by a speculative mind. It was discovered, waiting patiently within the core mathematics of our best theory of gravity. The universe's own laws seem to be suggesting a reality far stranger, far more balanced than our everyday experience could ever suggest. If the math insists on this symmetrical twin, then we are forced to confront a new and profound mystery. Could such a thing truly exist out there in the cosmos? Or is this a beautiful ghost, a mathematical mirage that reality simply refuses to manifest? This elegant mathematical symmetry, however, runs headlong into a brutal physical reality. If a black hole is born from a star's catastrophic collapse, what cosmic event gives birth to its opposite? A white hole presents a profound paradox of creation. It cannot form in the way we understand anything else forming. Think of it, a region of space that violently expels everything and forbids entry. How could such an object ever come to be in our universe, where everything seems to be falling together, not bursting apart? One audacious idea is that it didn't form at all, at least not in our timeline. Perhaps a white hole is not something that begins, but something that has always been. Imagine a singularity, a point of infinite density, simply appearing at the dawn of time, not as an end point, but as a starting gun. This is the concept of a primordial white hole, a theoretical fountain of matter and energy that could have erupted in the first moments of the cosmos, potentially even acting as a seed for the Big Bang itself. In this view, the white hole isn't an object in space. It is the original event, a cosmic geyser from which our entire universe may have flowed. Another, even stranger theory comes from looking at a black hole's far, far future. Our current physics hits a wall when trying to describe the final fate of a black hole. We know they evaporate over incomprehensible eons through a process called Hawking radiation, slowly leaking away their mass. But what happens at the very last instant when the final bit of mass and information is about to vanish? Some speculative models suggest the black hole doesn't just fade to nothing. Instead, it undergoes a dramatic transition, a cosmic rebound where the relentless inward pull of gravity finally exhausts itself and flips. The end point of collapse becomes a new point of eruption. The black hole, in its final moment, could theoretically transform into a white hole, offering a potential escape route for everything it ever swallowed. This idea pushes our understanding to the absolute limit, forcing us to consider that the arrow of time itself might loop back around in the most extreme environments. The formation paradox is more than a technical hurdle. It is a direct challenge to our linear understanding of cause and effect. It asks us to consider a universe where creation can be an explosive, singular event, and where an ending might secretly be a new kind of beginning. But this creation story collides with one of physics' most unbreakable rules. The second law of thermodynamics is the universe's great leveler. It states that entropy, a measure of disorder, always increases in a closed system. Things fall apart, energy spreads out, and neat structures inevitably decay into chaos. It's why a hot cup of coffee grows cold, why a sandcastle crumbles, and why you can't unscramble an egg. This law gives time its arrow, its irreversible direction from past to future. Now picture a white hole. It is a cosmic geyser, violently ejecting a torrent of matter and energy in a highly organized, focused outburst. At first glance, this looks like a blatant violation. Isn't it creating order from chaos, decreasing entropy, and essentially running the cosmic film in reverse? If true, it would shatter a foundational pillar of reality. So, does the white hole concept break the universe's most sacred law? The answer lies not in discarding the white hole, but in expanding our view of the entire process. A white hole cannot be an isolated event. In most theoretical models, it is intrinsically linked to a black hole, either as its symmetrical twin or its ultimate fate. Think of the black hole as the first act. When a star collapses to form one, it represents an astronomical increase in entropy. A complex, structured star is crushed into an incredibly simple object defined only by its mass, spin, and charge. All the intricate information about what fell in is, according to classical physics, lost to the singularity, creating a state of maximum disorder. The entropy of the universe skyrockets. Now, if that black hole were to somehow transform into a white hole in a distant future, that eruption would not be a free creation of order. It would be the final release, the payoff of a debt incurred long ago. The total entropy of the entire black hole to white hole cycle might still show a net increase, preserving the second law over the complete, unimaginably long timeline. This perspective is strengthened by the holographic principle, a revolutionary idea in theoretical physics. It suggests that all the information about what falls into a black hole is not destroyed at the singularity, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint. If the black hole evaporates or transitions, that information must somehow be preserved or returned. In this view, a white hole's eruption isn't creating new information. It is faithfully reading out a script that was written long ago on the surface of a black hole. The order it spews forth is just the reconstructed echo of a prior chaos. The thermodynamic tension, therefore, becomes a test of our models. It forces physicists to ask whether our understanding of entropy and information is complete. Does the second law hold across such radical transformations of spacetime itself, or does the white hole reveal a hidden loophole, a way for the universe to balance its books across the deepest chasms of gravity and time? This mystery doesn't kill the white hole idea. Instead, it elevates the stakes, turning it into a probe for the most fundamental laws governing existence. The most profound mystery of all may not be out in the distant cosmos, but in our own past. At the moment of the Big Bang, our entire universe is thought to have erupted from a single point of infinite density and temperature, a primordial singularity. Now hold that image in your mind and compare it to the theoretical heart of a white hole. What do we find? Another singularity, a point of infinite density from which matter and energy violently stream outward. The parallel is stunning, and it has led some cosmologists to a breathtakingly radical hypothesis. What if the Big Bang was not a unique, isolated event, but the functioning of a white hole on the grandest possible scale? In this view, our entire observable universe is not simply expanding into nothingness. We are living inside the ongoing eruption of a cosmic white hole. Every galaxy racing away from every other galaxy is not just expansion, it is the continued outflow from that initial singular event. This idea reframes everything. The Big Bang singularity was not a beginning from nothing, but a bridge from somewhere else. It becomes the white hole end of a wormhole connected to a black hole in a parent cosmos. Our universe, in this model, is the interior of that white hole, a new spacetime bubble that pinched off and began its own expansion. This leads to an even more profound concept known as cosmological natural selection, proposed by physicist Lee Smolin. Imagine a universe where black holes are not endpoints but cosmic nurseries. When a black hole forms in a parent universe and undergoes its final transition, it doesn't vanish. It rebounds as a white hole, giving birth to an entirely new baby universe within its core. This new universe inherits, with slight random variations, the fundamental physical constants of its parent. Over countless cycles, universes that produce more black holes become more prolific parents, spawning more offspring universes. Through this cosmic evolutionary pressure, the laws of physics themselves could be tuned toward the creation of black holes, and by extension, the conditions for new universes like our own. This mystery ties the fate of the smallest thing, a single collapsing star, to the largest thing, the entire cosmos. It suggests that the white hole is not merely a curious mathematical twin, but a potential engine of cosmic genesis. If true, then every black hole we see in our night sky is not a tomb, but a possible womb for an entire reality, a universe whose own night sky would be filled with the light of its own white hole beginning. But the idea of a white hole as a cosmic rebirth raises a deeper, more unsettling question. What if this transformation isn't just a grand cosmological event, but the inevitable fate of every single black hole? To answer that, we must venture to the very edge of known physics, to a place where our two most successful theories enter into open conflict. On one side stands Einstein's general relativity, which paints a majestic picture of curved spacetime and gravity. On the other stands quantum mechanics, which governs the bizarre, probabilistic world of the very small. For decades, these two pillars have refused to speak the same language, and nowhere is their battle more fierce than at the heart of a black hole. The quest to unite them is the search for a theory of quantum gravity, and it is here that the white hole may find its most compelling role. Stephen Hawking made a shocking prediction from this battlefield. He realized that the violent quantum fluctuations at the very edge of a black hole's event horizon should slowly leak energy, over timescales so vast they dwarf the current age of our universe. A black hole would evaporate particle by particle in a faint whisper now called Hawking radiation. This process solves one problem but creates a far worse one, known as the black hole information paradox. If a black hole evaporates completely, disappearing into a cloud of random radiation, what happens to all the detailed information about the stars, planets, and atoms that fell in? Quantum mechanics says information can never be truly destroyed. General relativity, with its crushing singularity, says it is obliterated forever. This paradox is a screaming alarm bell that our physics is incomplete. Some physicists propose a radical solution at the moment of evaporation's end. They suggest that when a black hole has shed nearly all its mass, the extreme quantum gravitational effects no longer allow for a true singularity. Instead of winking out of existence, the remnant, now smaller than an atom but still containing all that scrambled information, might undergo a quantum bounce. Imagine squeezing a spring to its absolute limit and then watching it rebound. In this scenario, the final act of a black hole's life is not a fade to black, but a flash of white. The inward collapse reverses into an outward eruption. The black hole transforms into a white hole. This microscopic white hole would then release, in that final burst of Hawking radiation, all the information it had locked away, thus preserving the quantum rulebook. Theories like loop quantum gravity, which attempts to describe spacetime itself as woven from tiny, discrete loops, naturally predict such rebounds. They suggest singularities are not points of infinite density, but regions of unimaginably high density where quantum gravity takes over and causes a bounce. In this view, every black hole contains the seed of its own white hole future, a cosmic phoenix waiting in the ashes of collapse. This mystery elevates the white hole from a mathematical curiosity to a potential savior of physics. It becomes the key mechanism that could resolve the information paradox, ensuring the universe remembers its own past. The white hole, therefore, isn't just about how universes might begin, but about how the deepest secrets of our own reality are ultimately preserved, not lost, in the darkest corners of space. A white hole doesn't just challenge our ideas about space, it attacks our understanding of time. Our most basic intuition tells us that causes come before effects. A seed is planted, then a tree grows, a star collapses, then a black hole forms. This forward march is the arrow of time, woven into our very perception of reality. But look at the white hole through that lens. It presents an effect without a clear cause in our timeline. Matter and energy erupt from a singularity, but what event, what action precipitated that eruption? If we trace its story backward, we seem to run into a wall, a beginning that has no prior cause. It is as if we are watching a cosmic movie played in reverse, where the explosion happens first and the reason for it is lost in the future. This is the Causality Conundrum, and it forces us to ask a disturbing question. Could time itself run backwards within or around a white hole? The mathematics of general relativity is famously time-symmetric. The equations work just as well if time flows forward or backward, which is precisely how the white hole solution is derived from the black hole. But does this mathematical symmetry describe a genuine physical possibility, or is it merely a trick of our coordinates, a ghost in the machine that reality filters out? Some physicists argue the latter, that the white hole represents an unstable mathematical configuration that the universe simply prohibits, much like balancing a pencil perfectly on its point. The slightest perturbation, the tiniest bit of matter trying to fall in, would cause it to collapse into a black hole, sealing the door and restoring the familiar flow of time. In this view, white holes are eternally forbidden objects because they violate the unbreakable chain of cause and effect we observe everywhere else. Yet, other theories dare to take the time symmetry seriously. They explore frameworks where such paradoxes might be resolved not by banning the white hole, but by redefining how causality works in the presence of immense gravity. One fascinating idea is the Novikov self-consistency principle. Proposed in the context of time travel, it suggests that the laws of physics simply do not allow paradoxes to occur. If you were to travel back in time, any action you took would already be a part of established history, woven seamlessly into the timeline. There are no alternate branches, no grandfather paradoxes, only a single, self-consistent loop. Apply this to a white hole. Its eruption, seemingly without cause, might actually be part of a larger, closed causal loop that we cannot see from our limited perspective. The matter it ejects could be the very same matter that formed the black hole it is connected to, in a cycle that has no true beginning or end in the way we understand it. Time in this scenario isn't a straight line with an arrow, but a knot. This conundrum pushes past the mechanics of gravity and into the realm of philosophy. What is time, really? Is it a fundamental river flowing in one direction, or is it an emergent property, a feeling that arises from the increase of entropy and the complex interactions of matter? The white hole, by threatening to reverse that flow, becomes a unique laboratory for questions we can barely phrase. It asks us to consider whether our cherished sequence of past, present, and future is a local condition or a cosmic absolute. The mystery of its causality may ultimately reveal that time itself is not the bedrock of reality we believe it to be, but a story the universe tells itself, a story that might, in the most extreme places, allow for a very different kind of plot. The greatest argument against white holes is not found in complex equations, but in the silent, star-filled sky above us. If these cosmic fountains are erupting somewhere, pouring out torrents of matter and energy, why is our universe not filled with their brilliant, unmistakable fireworks? This is the observational void, a profound and practical mystery that every theoretical idea must eventually confront. We have mapped black holes by watching stars whip around invisible points of immense gravity, and by listening to the ripples in spacetime when they collide. But for their theoretical twins, we have precisely nothing, no confirmed signal, no definitive flash in the cosmic dark. This silence is either a death knell for the idea or the ultimate clue, hinting that we have been looking in all the wrong ways. So, what would we actually see if a white hole suddenly flared into existence? Picture not a slow, a gentle welling up, but a cataclysmic birth scream. A white hole eruption would likely be one of the most violent and energetic events in the cosmos. From a single point, a focused jet of ultra-high energy radiation and fundamental particles would blast outward at nearly the speed of light. To our telescopes, this might appear as a sudden, intense flash of gamma rays, the most powerful form of light in the universe, outshining entire galaxies for a few fleeting seconds. It could resemble a gamma-ray burst, those mysterious beacons from the distant universe whose origins still puzzle astronomers. Or perhaps it would manifest as an incredibly powerful fast radio burst, a blip of radio waves lasting mere milliseconds, carrying the energy of hundreds of millions of suns. The signature would be brief, brilliant, and bizarre, a cosmic ephemera that vanishes almost as quickly as it appears. This very nature may explain our empty search. Perhaps white holes are not permanent structures at all, but transient events, flickering into existence and then vanishing or collapsing into something else almost immediately. Their entire lifetime could be a single, explosive pulse. We would have to be looking at exactly the right patch of sky at exactly the right millisecond to catch one. Another possibility is even more humbling. What if white holes were exclusively creatures of the ancient cosmos? In the seething, dense conditions of the early universe, moments after the Big Bang, the laws of physics may have allowed for these eruptions as a natural part of cosmic evolution. They could have been the seeds for the first structures, their brief lives over billions of years ago, their light long since faded into the microwave background static that fills all of space. We are simply living in a older universe where such primordial events no longer occur. There is a third, more subtle explanation. What if we have already seen them, but we called them something else? Astronomy is filled with energetic phenomena we do not fully understand. Certain hyper-energetic supernova, unexplained cosmic rays, or those enigmatic fast radio bursts could, in theory, be the observational fingerprints of a white hole event. Without a definitive theoretical model to compare against, we might be staring right at the evidence without recognizing it. The observational void, therefore, transforms from a simple absence of proof into a direct challenge. It asks us to refine our search, to look for the briefest flashes in new wavelengths of light, and to reconsider the catalogue of cosmic anomalies we have already collected. The silence is not necessarily a no. It might be a whisper waiting for us to learn how to listen. This brings us to one of the fiercest battles in modern physics, a conflict so fundamental it threatens to tear our understanding of reality apart. It is the black hole information paradox. Quantum mechanics, the rulebook for the subatomic world, states with absolute certainty that information can never be destroyed. Every detail about a particle, its spin, its charge, its history must be preserved. It can be scrambled, hidden, or transformed, but never erased from the cosmic ledger. Now place that rule against the classical portrait of a black hole. When a star, a planet, or even a book falls past the event horizon, general relativity says it is irretrievably crushed into the singularity. All the intricate information that made that object unique, the story of what it was, is seemingly obliterated. One law says the story must be saved forever. The other says it is burned in a gravitational fire. Both theories cannot be correct. This paradox is not a minor puzzle. It is a screaming alarm that our picture of the universe is broken, that somewhere in the marriage of the very large and the very small, we have made a catastrophic error. For decades, physicists have searched for an escape hatch, a mechanism that could rescue the information from the abyss. And here, the white hole emerges not as a curiosity, but as a potential hero. Imagine the final act of a black hole's epic life. After evaporating for eons via Hawking radiation, it reaches a microscopic size where quantum gravity takes command. In some models, this is the moment of the quantum bounce, the transformation from a black hole into a white hole. This is not merely a change of label. It is a fundamental reversal of destiny. The white hole, in its final, brilliant eruption, does not just spew random energy. It could act as a cosmic decoder, a fountain that releases not just particles, but the very information those particles carry. All the scrambled data that was thought lost at the singularity could be imprinted onto the outgoing Hawking radiation, faithfully transmitted back into the universe. This process would preserve what physicists call unitarity, the sacred quantum principle that the total information in a system must remain constant. The white hole becomes the universe's ultimate recycling plant. It takes in the chaotic debris of collapsed stars, processes it through the unfathomable physics of a bounce, and out puts a reconstructed history. In this view, a black hole is not a tomb. It is a temporary vault, and the white hole is the moment the vault door swings open, returning its contents to the cosmic ledger. This mystery positions the white hole at the very heart of the quest for a theory of quantum gravity. It is no longer just a symmetrical twin predicted by math, but a necessary component to make the math consistent. If our universe obeys quantum rules at every scale, then there must be a mechanism to preserve information, even from the most extreme gravitational prison. The white hole offers a breathtakingly elegant solution. It suggests that the universe has a built-in failsafe against forgetting, that even in the face of infinite density, the story of what fell in is never truly lost. It is merely waiting, encoded in the fabric of spacetime itself, for its moment to be told again. The most elegant vision of a white hole is not as a lonely fountain, but as one end of a cosmic tunnel. When mathematicians fully mapped the geometry of a Schwarzschild black hole, they didn't just find a pit and a fountain. They found a structure connecting them, a theoretical throat linking the two regions across the fabric of spacetime itself. This is the Einstein-Rosen Bridge, more popularly known as a wormhole. In this perfect mathematical picture, the black hole and the white hole are not independent objects. They are two mouths of the same passage. One mouth, the black hole, is an entrance nothing can exit. The other mouth, the white hole, is an exit nothing can enter. And between them stretches a bridge, a shortcut that could, in theory, connect two wildly distant points in the universe, or perhaps even two different universes altogether. This transforms the white hole from a mere curiosity into something far more profound, a potential gateway. For a fleeting moment, it offers the ultimate science fiction dream, a portal for interstellar travel. An astronaut could, in this idealized model, dive into the black hole mouth, and if they survived the crushing tidal forces, emerge from the white hole mouth in a completely different region of spacetime. It is a breathtaking idea, a built-in cosmic subway system suggested by Einstein's own equations. But the universe, it seems, abhors a free ride. This perfect wormhole bridge is tragically unstable. The moment any matter or energy tries to pass through it, the equations show the tunnel pinching off violently. The bridge collapses faster than light or anything else could traverse it, severing the connection and leaving the traveler trapped, not in a new world but in a singularity. In classical physics, the wormhole is a phantom, a structure that appears in the math but is physically impossible to cross. It is a door that slams shut the instant you reach for the handle. Yet, the dream of a traversable wormhole does not die so easily. Physicists have long speculated about what it would take to prop that door open. The key might lie in the bizarre realm of quantum physics or in hypothetical forms of matter with truly strange properties. One speculative idea involves exotic matter, a theoretical substance that possesses negative energy density. Unlike everything we see around us, which gravitates and pulls things together, exotic matter would exhibit negative pressure, a kind of gravitational repulsion. If such a substance could be found or created, it might be used to line the throat of a wormhole, acting as a sort of anti-gravitational scaffolding to keep the tunnel from collapsing long enough for something to pass through. Another possibility is that quantum effects, which dominate at the tiniest scales, could stabilize a microscopic wormhole at the Planck scale, the fundamental length of the universe. While this would be far too small for any human travel, it hints that the principle of connectivity might be woven into the quantum foam of spacetime itself. The wormhole bridge concept, therefore, elevates the white hole from an isolated oddity to a central piece in a grander architectural blueprint of the cosmos. It suggests that the most extreme objects in the universe might not be dead ends, but connectors, woven into a hidden network of shortcuts our classical physics can barely perceive. While we have no evidence such traversable bridges exist, their theoretical possibility forces us to reconsider the very topology of reality, asking if the universe is far more interconnected and far more strangely shaped than our lonely perspective from one small planet has ever allowed us to see. But this dream of a stable gateway runs on a fuel stranger than any star. To prop open a wormhole throat or to prevent a white hole from instantly collapsing, the equations demand something utterly alien, a substance known as exotic matter. This is not just rare or unusual material. It is matter that defies one of the universe's most basic rules. Normal matter, everything from stars to stardust, possesses positive energy density. It warps spacetime inward, creating the gravity that pulls things together. Exotic matter would have negative energy density. Think of it as a kind of gravitational antigravity. Instead of pulling, it would push, exerting a repulsive pressure that could, in theory, counteract the crushing force trying to snap a wormhole shut or seal a white hole's exit. It sounds like pure science fiction, but the concept finds a whisper of validation in a well-established quantum quirk called the Casimir effect. In the emptiness of a perfect vacuum, quantum physics tells us that virtual particles are constantly flickering in and out of existence. Now place two incredibly smooth, uncharged metal plates extremely close together in that vacuum. The plates restrict which kinds of virtual particles can appear in the narrow gap between them. This creates a subtle imbalance where the quantum activity outside the plates is slightly greater than the activity inside. The result is a measurable, tiny force that pushes the plates together. From the perspective of the space between the plates, this can be interpreted as having a negative energy density. It is a fleeting, microscopic hint that the universe does allow for such conditions under strict quantum rules. So, could the violent maelstrom at a white hole's horizon naturally generate the exotic matter needed to sustain itself? The environment there is one of unimaginable strain, where spacetime is stretched and quantum effects are magnified to cosmic scales. Some models suggest that the very process of Hawking radiation, the quantum leakage from the horizon, involves temporary states of negative energy. It is conceivable that in the final, frantic moments of a black hole's quantum bounce into a white hole, these effects could become dominant, creating a self-sustaining bubble of exotic physics at the eruption's heart. This requirement for negative energy is not a minor detail, it is a fundamental revelation. It shows that white holes are not just testing our theories of gravity, they are probing the absolute limits of material reality. They ask whether the universe permits, even for an instant, a state of being where gravity itself flips its sign, where the fabric of space pushes rather than pulls. If such conditions cannot arise naturally, then perhaps traversable wormholes and stable white holes are forever locked away in the realm of mathematical elegance. But if they can, even for a fleeting quantum moment, then the cosmos may be far stranger and far more open than we ever dared to dream. Einstein's general relativity is a masterpiece, but it is not the final word on gravity. As physicists push beyond its horizons, searching for a theory that can also embrace the quantum world, they find the white hole waiting for them there too. It is a concept so resilient that it emerges, transformed but recognizable, in nearly every serious attempt to rewrite the rules of the cosmos. Take Brans-Dicke theory, an early and influential alternative to general relativity. It introduces a dynamic field that interacts with gravity, a kind of cosmic dial that can change from place to place and over time. In this framework, a white hole would not be a simple mirror image of a black hole. Its properties, its lifetime, even the very energy of its eruption could be subtly or dramatically different, tuned by that additional cosmic field. This tells us the white hole is not a prisoner of one specific set of equations. It is a shape that spacetime can take under many different governing principles. Another class of theories, called F(r) gravity, modifies Einstein's framework by allowing gravity itself to behave differently at extreme scales. Instead of the curvature of spacetime always responding to matter in the same way, the relationship becomes more complex, like a spring that stiffens the harder you press. In such a universe, the dynamics of a white hole could change profoundly. Its eruption might be less violent, more prolonged, or it might interact with the fabric of the cosmos in ways that leave a distinct, observable signature. These alternative theories are not mere curiosities. They are stress tests for the white hole concept, proving its mathematical robustness across different visions of reality. But the most profound reinvention of the white hole idea comes from a leading candidate for quantum gravity itself, loop quantum cosmology. This theory applies the principles of loop quantum gravity to the universe as a whole. And here it performs a miracle. It erases the most troubling singularity of all, the Big Bang. In Einstein's framework, the beginning of everything is a point of infinite density where the laws of physics break down. Loop quantum cosmology replaces that mysterious beginning with a transition, a cosmic rebound it calls the Big Bounce. Picture our universe not exploding from nothing, but contracting from a previous, larger cosmos until it reaches a point of immense but finite density. There, quantum gravitational effects become so powerful that they generate a repulsive force, turning the collapse around into a new expansion. This moment, the heart of the Big Bounce, is not a singularity. It is a quantum white hole event on a universal scale. Our entire cosmos, in this view, is the interior of a white hole born from the collapse of a prior universe. This elegant solution does more than sidestep a mathematical infinity. It embeds the white hole mechanism into the very origin of everything we see. It suggests that the universe itself may be cyclical, with each great contraction ending not in a silent crush, but in a creative roar, a white hole giving birth to a new reality. The persistence of this idea across so many frontiers of theoretical physics is a powerful clue. It tells us we are not chasing a phantom, but tracing the outline of a deep and fundamental feature of reality, one that appears whenever we dare to look beyond the known. This dance of collapse and creation forces us to confront a profound philosophical question about the universe's ultimate character. For over a century, the narrative of modern cosmology has leaned toward a kind of cosmic fatalism, a story with a cold and quiet end. We see the second law of thermodynamics everywhere, the inevitable slide from order to disorder. Stars burn out, galaxies drift apart, and all useful energy will one day be spread thin. This is the heat death, a future where the cosmos reaches a state of maximum entropy, a uniform, lukewarm sea of particles where nothing happens forever. In this view, black holes are the ultimate emblem of this fate, the final sinks where matter and light are consumed, their stories erased in a silent gravitational grave. They represent an ending with no sequel, a universe winding down. But then we have the white hole, this theoretical fountain. Its very possibility, even as a mathematical ghost, introduces a radically different note into the cosmic symphony. It is a symbol not of consumption but of creation, not of an ending but of an emergence. It whispers of potential renewal, of a universe that might not simply run down, but could, in its most extreme precincts, turn a corner. The concept suggests that entropy's victory may not be absolute, that there could be mechanisms, however exotic, for regeneration built into the fabric of reality itself. This idea of cyclical rebirth is not new to human thought. It echoes through countless ancient cosmologies, from the Hindu concept of cosmic cycles unfolding over billions of years, to the phoenix rising from its own ashes, to philosophical traditions that speak of eternal return. For millennia, these were metaphors, stories we told to make sense of time and existence. What is startling is that our most advanced mathematics, in its search for a complete theory of quantum gravity, is now whispering a similar story. The white hole and the cosmological bounce it implies offers a scientific narrative where the universe itself might be cyclic, where a great contraction leads not to nothingness but to a new beginning. This does not offer sentimental comfort or promise immortality. The scales are incomprehensibly vast, the processes violent and alien, but it does challenge a purely entropic, one-way view of cosmic destiny. It suggests the universe may have a deeper resilience, a capacity for reinvention written into its most fundamental laws. The philosophical weight of the white hole, therefore, lies not in proving we will live again, but in expanding our imagination of what is possible. It asks us to consider whether the cosmos is a single, tragic play moving toward a final curtain, or something more like an endless, evolving tapestry, where endings in one thread are woven into the beginnings of another. The equations of general relativity may have given white holes a name, but it was human imagination that gave them a story. Long before they were debated in physics journals, the essence of this idea, the fountain of creation, the cosmic exit door, began to seep from theoretical papers into the bedrock of our science fiction. This cultural adoption reveals something profound, not about the universe but about us. When science offers a strange new shape, storytellers rush to explore what it might mean for destiny, for hope, and for the very nature of existence. Perhaps the most famous literary appearance is in Arthur C. Clarke's sequel to 2001, A Space Odyssey, titled 2010, Odyssey 2. In this narrative, the mysterious monoliths surrounding Jupiter trigger a transformation, collapsing the giant planet into a miniature star to warm its moons. But Clarke, with his deep engagement with scientific speculation, took the idea a breathtaking step further. He proposed that the vanished planet Jupiter didn't just become a star, it became a gateway, a white hole named Lucifer, ejecting its transformed matter into another universe entirely. Here, the white hole is not merely a plot device, it is a mechanism for transcendence, a literal bridge to a higher plane of reality for the story's characters. It serves as the ultimate deus ex machina, but one rooted in a tantalizing scientific maybe, granting a sense of awe that feels earned rather than arbitrary. Across the long-running television series Doctor Who, white holes have appeared multiple times as cosmic anomalies and power sources. In one classic serial, the Doctor discovers a white hole serving as the energy heart for an ancient city, a battery of pure creation. In another, it is a dangerous temporal anomaly. Their narrative function shifts, but the core concept remains, a source of immense, often uncontrollable power that can rewrite local reality, create pathways, or serve as a weapon. This versatility is key. In fiction, the white hole becomes a tool for storytelling about genesis and escape. It is a plot engine for birthing new worlds, for providing a last-minute exit from a doomed reality, or for explaining the origin of mysterious cosmic phenomena. This cultural journey from equation to episode demonstrates how the white hole captures a fundamental human longing. It is a metaphor for the reversal of fortune, for the hope that from absolute collapse, something new and wondrous can erupt. It speaks to our innate desire for second acts, for the universe to contain not just endings, but also beginnings hidden within those endings. When a writer uses a white hole, they are tapping into that deep-seated narrative archetype of the phoenix, but giving it the gloss of scientific plausibility. The concept allows for stories that feel both cosmically vast and strangely personal, where the laws of physics themselves can facilitate rebirth and redemption. This cultural legacy is a vital part of the white hole story. It proves that the idea holds a power that transcends mathematics, resonating with our most ancient stories about cycles, creation, and the unexpected ways light can emerge from the darkest places. Yet the search for these cosmic phoenixes is not confined to telescopes alone. Some of the most profound insights are emerging not from deep space, but from deep within the laboratory, where physicists are building miniature, analog versions of the universe's most extreme phenomena. Since we cannot create a true gravitational singularity on Earth, scientists have turned to a brilliant workaround, using the behavior of other physical systems to mimic the strange physics of horizons. This field is known as analog gravity, and it allows us to simulate the conditions of a white hole in a controlled setting, using something as simple as flowing water. Imagine a fast-moving stream of water flowing toward a waterfall's edge. Now, imagine sending a small ripple, a wave, upstream against that current. If the water is flowing faster than the ripple can travel upstream, the wave will be swept backward over the edge, unable to make progress. In this scenario, the point where the water's flow speed matches the wave's speed acts exactly like an event horizon. For the wave, it is a point of no return, a one-way street leading only toward the waterfall's plunge. But what if we reverse the setup? Picture a powerful fountain, a jet of water erupting upward and then cascading down in all directions. If you try to send a surface ripple inward toward the central jet, you might find a point where the outward rushing flow is so strong that the ripple cannot penetrate it. The ripple hits an invisible wall in the water, a boundary it cannot cross from the outside. This, in the language of fluid dynamics, is an analog white hole horizon. Nothing from the external pool can enter the erupting central region. These elegant water tank experiments provide a tangible, visual model for how horizons can emerge not from gravity, but from the flow of a medium. They allow researchers to study how waves behave when they interact with these boundaries, probing the complex interplay of energy and information. But the simulations can go much further into the quantum realm. In ultra-cold labs, physicists work with a state of matter called a Bose-Einstein condensate, where atoms are chilled to near absolute zero and begin to behave as a single quantum wave. By carefully manipulating this condensate, scientists can create flows and barriers that mimic spacetime curvature. In such a system, they can engineer an analog event horizon and then look for the telltale signs of the analog of Hawking radiation, the spontaneous creation of particle pairs at the horizon. Remarkably, several experiments have reported detecting signatures consistent with this analog radiation, a breakthrough that suggests the quantum effects predicted for black holes are not just mathematical fantasies, but robust phenomena that appear in many kinds of horizon physics. Other researchers use pulses of light in nonlinear optical materials, where the properties of the medium change with light intensity, creating effective horizons for other light waves. These optical analogs act as high-speed test beds for how information might scramble or be preserved at a boundary. While these lab creations are not true white holes warping spacetime itself, they are powerful analog computers. They let us run experiments on horizon physics every day, testing the universality of concepts like Hawking radiation and information flow in a system we can control, measure, and tweak. Each successful measurement in a tank of water or a cloud of super-cold atoms is an indirect clue, a piece of evidence that the strange rules governing black holes and their theoretical twins are not merely artifacts of one specific theory, but may be fundamental features of any system that contains a causal boundary. They give us reason to believe that the mathematics describing white holes is describing something real, a pattern that nature repeats across wildly different scales and mediums. The early universe was a canvas of near-perfect smoothness, a searing hot plasma with only the tiniest of ripples in its density. Yet from that primordial uniformity, everything we see today emerged, the vast cosmic web of galaxies and clusters. The great mystery of cosmology is what planted those first seeds, the initial imperfections that gravity could amplify into the structures of the modern cosmos. The mainstream answer for decades has been a process called cosmic inflation, a period of unimaginably rapid expansion in the first fraction of a second that stretched quantum fluctuations to cosmic scales. But what if there was another, more dramatic gardener at work in that ancient dawn? This is the primordial white hole hypothesis. Imagine not a gentle stretching of space, but a series of violent, pinpoint eruptions scattered throughout the infant cosmos. Each primordial white hole, a fountain of matter and energy erupting from a singularity, would have been a cosmic bomb of organization. Its explosive output would have created a powerful shockwave in the surrounding plasma, a localized region of higher density. Think of tossing a handful of stones into a perfectly still pond. Each stone creates a ripple, a disturbance that spreads outward and interacts with the others. In the hot soup of the early universe, each white hole eruption would have been such a stone. The resulting density ripples, these scars from ancient outbursts, could have served as the gravitational seeds around which dark matter and normal matter first began to clump. Over billions of years, these clumps would have grown through mutual attraction, eventually collapsing into the first stars, the first galaxies, and the great filamentary walls we map today. In this speculative vision, white holes are not merely endpoints or oddities. They become the potential architects of cosmic structure, the chaotic sculptors that gave the universe its shape. This idea stands in stark contrast to the inflationary paradigm, which relies on the smooth, quantum mechanical stretching of the entire fabric of space. Inflation is elegant and mathematically powerful, explaining the large-scale smoothness and the specific pattern of the cosmic microwave background with remarkable precision. The white hole hypothesis is messier, more explosive, and far less developed. It lacks the comprehensive predictive framework of inflation, yet it persists as a fascinating alternative, a reminder that our origin story may still hold room for more violent, more discrete acts of creation. Could the majestic cosmic web we trace across the heavens be the fossilized imprint of countless white hole births, a permanent record of the universe's most creative explosions? It is a question that pushes white holes from the fringe of theoretical physics directly into the heart of cosmology, challenging us to consider whether the largest structures of all were built not from a whisper, but from a shout. The mystery of dark matter is a ghost haunting the heart of modern cosmology. We see its gravitational hand everywhere, bending light from distant galaxies and holding spinning clusters together. Yet it refuses to interact with light itself, remaining utterly invisible. For decades, scientists have searched for its identity, from exotic subatomic particles to faint, failed stars. But what if the answer is not a new form of matter, but an old, forgotten shape in spacetime? This speculative idea asks a startling question. Could dark matter be made, at least in part, from the remnants of primordial white holes? If these cosmic fountains erupted in the universe's first moments, they would have been incredibly dense, compact objects. After their brief, violent outburst, they might have left behind inert, massive relics, dark cinders scattered throughout the cosmos. These remnants would possess mass and exert gravity, but with no ongoing eruption, they would emit no light, perfectly matching the description of a dark matter candidate. It is a beautifully elegant possibility, linking one profound cosmic mystery directly to another, but elegance must face the harsh scrutiny of observation. Astronomers have powerful tools to test whether dark matter could be made of compact objects like black holes, and by extension, white hole remnants. One key method is gravitational microlensing. When a massive, compact object passes in front of a distant star, its gravity acts as a lens, bending the star's light and causing a temporary, characteristic brightening. By monitoring millions of stars for these telltale flashes, surveys have placed severe limits on how much of the dark matter could be lurking in the form of black holes within a certain mass range, particularly between the mass of a large asteroid and that of a star. The data suggests that while such objects might exist, they cannot account for the vast majority of dark matter's gravitational influence. This seems to rule out a universe filled with ancient black hole fossils. However, a white hole remnant is not a black hole. Its formation and life cycle are theorized to be fundamentally different. A key constraint on black holes as dark matter comes from their potential to alter the cosmic microwave background, the afterglow of the Big Bang. If numerous black holes were evaporating via Hawking radiation in the early universe, they would have injected extra energy, distorting that pristine microwave signal in ways we do not observe. But a stable white hole remnant, one that has finished its eruption and now simply sits there as a gravitating mass, would not evaporate. It would be silent and dark, potentially evading this crucial microwave background test. Furthermore, its initial eruption would have happened in the ultra-dense early universe, a context so extreme that its effects might be indistinguishable from other violent primordial processes. This speculative identity forces us to look at the dark matter puzzle from a radically different angle. We are not searching for a particle, but for a fossil, a relic of a creative act that helped shape the cosmos. The constraints from microlensing and the cosmic microwave background are not necessarily death blows, but signposts. They tell us that if white hole remnants are out there, they must exist in a specific mass window or possess properties that make them effectively invisible to our current searches. This mystery, while highly speculative, is profoundly useful. It demonstrates how the white hole concept can be a tool for thought, a way to stress-test our assumptions about what forms the unseen foundation of reality might take. It challenges us to consider whether the missing mass of the universe is something entirely new, or something incredibly old, a silent echo from the first instance of creation, when the universe may have been filled with the brilliant, brief fire of white holes. Beneath the smooth geometry of planets and stars lies a far wilder reality. At the tiniest imaginable scale, the very fabric of space and time is not calm and continuous, but a seething, turbulent ocean. This is the quantum foam, a concept born from the attempt to marry gravity with quantum mechanics. Here, at distances a million billion times smaller than an atom, the orderly predictions of general relativity break down. Spacetime itself becomes probabilistic, fluctuating and frothing with unimaginable energy. In this chaotic, fundamental substrate, the distinction between something and nothing blurs. And according to some daring theoretical models, this is where white holes might find their most natural, if fleeting, home. Within this quantum foam, pairs of virtual particles are not the only things that can spontaneously appear. The extreme fluctuations in energy and geometry could, for the briefest instant, twist spacetime into microscopic tunnels and pinprick singularities. It is theorized that virtual black holes and their twins, virtual white holes, could constantly pop into existence, linked by ephemeral wormholes, only to annihilate each other a moment later. Picture a bubbling pot of water on a cosmic scale, where each bubble is not air, but a complete, self-contained distortion of reality, a tiny universe of extreme physics that winks into and out of being before it can ever be measured. In this dizzying perspective, white hole behavior is not a rare, catastrophic event waiting in deep space. It becomes an integral, if ephemeral, part of the bedrock of reality itself, woven into the quantum weave of spacetime. At this scale, even causality becomes fuzzy. The clean sequence of cause and effect that governs our world dissolves into a network of probabilities. A virtual white hole eruption in the foam might be the cause of a linked black hole's formation, or it might be the effect, with the two events locked in a loop that has no true beginning or end from our macroscopic viewpoint. This suggests that the universe at its heart might be a dynamic tapestry of connections with microscopic bridges constantly forming and dissolving. The grand, stable white holes of cosmology could then be seen as rare, amplified versions of these ever-present quantum tremors, a tiny foam bubble that, through some unknown mechanism, managed to inflate and persist. While we cannot probe this Planck-scale realm directly, its theoretical existence forces a profound shift in how we view cosmic architecture. It implies that the potential for creation and destruction for black holes and white holes is not an added feature to the universe, but is baked into its very substance, a permanent whisper of possibility churning beneath the apparent calm of the cosmic void. But this beautiful symmetry of the Einstein-Rosen Bridge hides a fatal flaw. The most significant theoretical objection to a lasting white hole is not its creation, but its survival. The mathematics suggests these cosmic fountains are profoundly unstable, perhaps existing for only the briefest instant before the universe itself shuts them down. To understand why, we must consider a simple, inevitable intruder, a single speck of interstellar dust drifting through the void. From our perspective outside a white hole, this dust particle cannot cross the event horizon. It is forbidden from entering, repelled by the one-way nature of that boundary. But from the perspective of the dust particle itself, following its own path through spacetime, the story is very different. As it approaches the horizon, general relativity tells us that time and space trade roles in a dizzying swap. The particle's forward march in time, from its own point of view, becomes a movement deeper into the white hole's interior. To an outside observer, however, the particle appears to slow down, freezing at the horizon, its image red shifted into oblivion over an infinite amount of our time. This creates a bizarre contradiction. The energy of that frozen, infalling particle from our external reference frame would become infinite as time stretches on. An infinite energy barrier would effectively form at the horizon. Physics abhors such infinities. The prevailing theory, supported by physicists like Igor Novikov, is that this instability is catastrophic. The mere attempt of anything, even a single atom, to fall into the white hole would trigger a fundamental transformation. The infinite blue shift of that infalling matter's energy would act like a sledgehammer blow to the delicate structure of the white hole horizon. In response, the geometry would reconfigure itself, the exit door would seal shut, and the fountain would collapse inward. The white hole, in a cosmic instant, would transform into a black hole. This is not a gradual change, but a sudden phase transition in the fabric of spacetime itself. The implication is staggering. It suggests that a stable, permanent white hole is a mathematical ideal that reality cannot sustain. The universe seems to have a built-in censorship program, a law that forbids such a blatant reversal of causality from persisting. Any white hole that managed to form, whether from a quantum bounce or a primordial seed, would be under immediate siege by the vacuum itself. Virtual particles, quantum fluctuations, or any stray bit of matter in its vicinity would spell its almost instantaneous doom. Therefore, if white holes exist at all, they are not enduring cosmic structures. They are ephemeral events, cosmic flashes in the pan. Their entire lifetime could be a single, brilliant pulse of eruption before the universe enforces its rules and collapses them back into the more familiar, more stable form of a black hole. This profound instability may be the ultimate answer to the observational void. We do not see white holes not because they are impossible, but because they are impossibly brief. They are the universe's most spectacular mayflies, born shining and dying in a moment, leaving behind only a transformed geometry or a fading echo of radiation. Their elusiveness is not a mark against them, but a signature of their nature, a testament to a cosmos that allows for miraculous possibilities, but only for the blink of a cosmic eye. The holographic principle is one of the most radical ideas to emerge from the battle between gravity and quantum mechanics. It proposes a profound simplification of reality, suggesting that all the information contained within any volume of space, the full three-dimensional dance of particles and forces, can be perfectly encoded on its two-dimensional boundary, like a cosmic DVD. The three-dimensional world we experience would then be a projection, a hologram, emanating from that lower dimensional surface. This isn't just a metaphor for black holes, it is a potential law for the universe itself. And when we turn this lens toward a white hole, the implications are nothing short of breathtaking. Apply the holographic principle to this cosmic fountain. Its violent, churning interior, full of erupting matter and twisted spacetime, might not need to be described particle by particle. Instead, every bit of information about what is happening inside, the entire history of the eruption, could be written in a quantum language on its event horizon. That forbidding boundary, the one-way exit door, becomes a luminous screen, a quantum film reel playing out the story of the white hole's creation. In this framework, the white hole is no longer a mysterious classical object defying physics. It transforms into a specific, well-defined quantum state of geometry and matter. Its existence becomes a question of information processing, a particular arrangement of quantum bits on a surface. This perspective solves several thorny problems at once. First, it offers a consistent quantum mechanical description of a white hole, something that has eluded physicists working with classical equations. By treating it as a quantum state on a horizon, we can use the tools of quantum field theory and information science to understand its properties, its stability, and how it might interact with the rest of the universe. Second, it beautifully complements the idea of a white hole as the rebirth of a black hole. Remember, the holographic principle suggests that a black hole stores all the information of what fell in on its event horizon. If that black hole then undergoes a quantum bounce into a white hole, that encoded information doesn't vanish. It simply becomes the script for the new eruption. The white hole's horizon reads out that stored data, projecting it back outward as the reconstituted matter and energy we see spewing forth. The white hole, in this view, is a black hole's memory made manifest. It also reframes the white hole's instability in an intriguing way. Perhaps the transition from a black hole state to a white hole state on the holographic screen isn't a violent geometric upheaval, but a quantum computational process, a rewriting of the code on the boundary. The instability to external matter might then be seen as a form of quantum decoherence, where an external interaction corrupts that delicate computational state, causing it to collapse into the more stable, absorbing state of a black hole. This holographic approach doesn't make white holes more likely, but it does make them more comprehensible within our most advanced theories of reality. It suggests that if they are possible, they are not glitches in the universe, but valid entries in the cosmic quantum ledger, specific and rare arrangements of information on the fabric of spacetime itself. The search for a white hole, then, becomes a search for a very specific signature in the quantum data of the cosmos, a pattern of information that means not consumption but creation. The holographic screen of a white hole might not be projecting into our universe at all. Some interpretations of its geometry take us to a place far stranger than distant galaxies. When we trace the path through the theoretical tunnel of an Einstein-Rosen Bridge, the white hole mouth does not necessarily open back into our own cosmos. Instead, it could be a doorway into a completely separate reality, a universe with its own distinct physical laws and history. This transforms the white hole from a fountain into a gateway, a cosmic umbilical cord connecting one reality to another. The idea finds a startlingly natural home within the multiverse hypothesis. Consider eternal inflation, a theory that our Big Bang was not a unique event, but one bubble in a frothing, infinite sea of expanding spacetime. In this endless, inflating meta-universe, new bubble universes are constantly nucleating, each with its own random set of physical constants. How does a new bubble form and detach? The violent, singular eruption of a white hole provides a compelling mechanism. In this picture, a white hole is not an object within a universe, it is the birth event of an entire new universe. Our cosmos, with all its galaxies and stars, could be the interior of a white hole that formed in a parent cosmos, its eruption defining our own Big Bang. This elegantly sidesteps the question of what came before, suggesting we are living inside a cosmic offspring. String theory adds another layer to this landscape. Its mathematical framework suggests a vast number of possible stable configurations for the extra dimensions it proposes, each configuration corresponding to a universe with different laws. This is the string theory landscape, a cosmic catalog of possible realities. A white hole tunnel could be a conduit between these different points in the landscape, a rare bridge where the fabric of one stable vacuum state connects to another. The matter erupting from the white hole would not just be random energy, it would be the seed of a new physics, a new set of rules blossoming into its own self-contained reality. Within these frameworks, every black hole in our universe takes on a staggering new potential. When one forms from a collapsing star, it might not be a final grave. In its distant future, through a quantum bounce or a tunnel, it could become the white hole genesis point for an entirely new universe, hidden forever from our own. This makes the cosmos not just a collection of stars, but a fertile, branching tree of realities, where the end of one story is forever linked to the beginning of another. The white hole as a multiverse gate challenges our deepest notions of isolation. It suggests our reality may not be alone, but connected through hidden, singular threads to a family of universes we can never see, each born from a moment of impossible creation. This cosmic vision of endless creation inevitably turns our gaze inward. If universes can be born from the ashes of collapse, if a white hole can rewrite an ending as a beginning, what does that whisper about our own story? We are, after all, beings born from stellar cataclysm, our very atoms forged in the hearts of stars that lived and died long ago. Our origin is already a tale of destruction giving way to creation, of an ending seeding a new possibility. The white hole, in its most philosophical light, mirrors a pattern we recognize not just in the heavens, but in the very rhythm of life on our own world. Think of a forest fire, a seemingly final act of devastation. Yet from the scorched earth and nutrient-rich ash, new seedlings sprout with relentless vigor, often healthier and more diverse than what came before. The fire was not merely an end, it was a harsh, necessary reset for the ecosystem's next chapter. Societies and cultures, too, experience this cycle. Periods of great hardship or conflict can shatter old structures, creating a painful void. Yet from that void, new ideas, innovations, and forms of community often emerge, reshaping the human story in unexpected ways. The white hole serves as a powerful scientific metaphor for this deep-seated resilience. It suggests that the potential for a new beginning is not a sentimental hope, but a principle that may be woven into the fabric of reality itself, from the quantum scale to the cosmic. It challenges the finality we often assign to endings, asking us to consider whether an endpoint is ever truly absolute, or merely a transition we cannot yet see beyond. This isn't to diminish loss or struggle, but to frame them within a broader, more enduring context. The contemplation invites a quiet shift in perspective. When we face personal conclusions, the closing of a chapter, or a moment that feels like a definitive crash, the white hole metaphor offers a different lens. It doesn't promise a magical reversal, but it hints that the universe's repertoire is vast and surprising. What seems like an inescapable collapse might, in some form we cannot yet perceive, contain the seed of a different kind of eruption, a reorganization leading to a new state of being. Our own origins, from stardust to consciousness, are proof that the universe specializes in such astonishing transformations. So while we may never witness a white hole flaring in the distant void, its theoretical possibility enriches our understanding of existence. It reminds us that creation and destruction are not opposites locked in war, but partners in an endless, intricate dance. The story of the cosmos, and perhaps our own small part within it, may be less about avoiding the fall, and more about learning to recognize the potential for light that can follow, even from the deepest dark. The hunt for a white hole will not rely on luck, but on a new generation of cosmic detectives. These are not single telescopes, but vast networks of instruments listening to the universe in every language it speaks, from the faintest ripples in spacetime to the highest energy particles screaming across the cosmos. Their mission is to catch the ephemeral, and a white hole's death or birth could leave a signature unlike any other. The most profound clue might be written in gravity itself. If a black hole undergoes a quantum bounce to become a white hole, that moment of transition, that sudden reversal from implosion to explosion, would send a shock wave through the very fabric of reality. This gravitational wave signal would be unique, a sharp pop or a resonant ring following a collapse, utterly distinct from the merging chirp of two black holes or the crash of neutron stars. Future observatories like the Laser Interferometer Space Antenna, or LISA, a fleet of spacecraft forming a gravitational wave observatory in space, will be exquisitely tuned to lower frequencies than our ground-based detectors. It could hear the deep, rumbling echoes of such an event from the dawn of time or from the quiet corners of our modern galaxy. Simultaneously, the eruption would be a factory for ghostly particles. Neutrinos, those nearly massless particles that stream through matter unimpeded, would flood out from the heart of the event. A sudden, intense burst of high-energy neutrinos arriving from a single point in the sky, with no accompanying explanation like a supernova, would be a screaming siren for theorists. Next-generation neutrino observatories buried deep in ice or under the sea are already listening for such whispers from the abyss, and then there is the light. The initial flash could be a gamma-ray burst, but its afterglow might hold anomalies. The spectrum of light, its specific colors and energies, could show strange chemical abundances or energy distributions that don't match any known stellar explosion. The Vera C. Rubin Observatory, with its panoramic eye that will scan the entire visible sky every few nights, is designed to catch such transient flashes, these cosmic mayflies that appear and vanish before other telescopes can even turn. It will compile a vast movie of the changing sky, and within that movie, a white hole's brief, brilliant cameo might be hiding. Advanced radio telescopes, like the Square Kilometre Array, will listen for the radio echoes of such an event, the long-lasting reverberations in the magnetized plasma surrounding it. These observatories together form a web of perception. They turn the philosophical speculation of a white hole into a concrete scientific search. We are no longer just asking if they can exist, we are building the tools to ask the universe directly. The next great discovery in astrophysics may not be an object we can see, but a pattern we learn to recognize, a specific confluence of a gravitational wave pop, a neutrino shower, and a strange flash of light, all telling the same story of a collapse that turned inside out. The silence of the cosmos may be about to break, and when it does, we will have an army of detectives ready to decode its message. The equations on the page can only take us so far. To truly test whether spacetime can turn itself inside out, we must build universes inside machines. In the silent halls of research institutions, the most powerful supercomputers on Earth are running simulations of realities that may or may not exist, performing digital experiments on the very edge of known physics. This field is called numerical relativity, and it is our most powerful tool for visualizing the invisible. Researchers feed Einstein's complex equations into these vast networks of processors, setting initial conditions that describe a collapsing star or a spinning black hole. The computer then calculates step by tiny step how spacetime curves, twists, and evolves under those extreme forces. It is a process of brute force discovery, watching geometry come to life on a screen. These simulations have already revolutionized our understanding of black hole mergers, accurately predicting the gravitational wave signals we later detected. Now they are being directed at an even more elusive target. Scientists can tweak the starting parameters, asking the digital universe a profound what-if. What if the inward rush of matter at a singularity reached a point of maximum compression and then rebounded? The simulation doesn't know it's impossible, it just calculates the consequences. In some models, the result is a dramatic reversal, a burst of energy and curvature propagating outward, a digital white hole eruption flickering into existence on a graph. These simulations are crucial for understanding the white hole's fatal instability. By introducing even a single virtual particle of matter near the horizon, researchers can watch in exquisite detail how the geometry responds, how the repulsive barrier breaks down, and how the fountain collapses back into a sink. It is a digital proof of concept for why these objects might be so spectacularly fleeting. Beyond classical gravity, other teams are using supercomputers to simulate the fuzzy realm of quantum gravity itself. Using approaches like loop quantum gravity or causal dynamical triangulation, they are not simulating smooth spacetime, but building it from the ground up from billions of tiny, discrete geometric units, like pixels on a cosmic screen. In these digital quantum universes, they look for the conditions that could cause a bounce, a natural transition from a black hole state to a white hole state, governed by quantum probabilities rather than classical forces. Could quantum effects create a stable, microscopic throat, a wormhole held open long enough to be traversable, even for a fraction of a second? The supercomputer grinds through quintillions of calculations to provide a statistical hint. While no simulation can yet definitively prove a white hole's reality, each one acts as a rigorous stress test. They map the landscape of possibility, showing us which mathematical pathways lead to collapse, which might lead to a brief eruption, and which are forever forbidden by the deeper logic of the cosmos. In the absence of a telescope image, these glowing datasets and evolving visualizations are our closest windows into a reality where creation and destruction are two sides of the same coin, playing out in the silent, relentless logic of pure computation. The universe is not a museum of isolated curiosities. It is a dynamic, breathing ecosystem where every extreme phenomenon is a thread in a single, vast tapestry. White holes, in their most profound light, are not cosmic monsters or mathematical ghosts living in isolation. They are a potential phase in the life cycle of spacetime itself, one note in a grand cosmic chord that includes black holes, wormholes, and the very birth of our reality. To see them this way is to shift our entire perspective from cataloging objects to understanding processes. Think of a forest. You can list the trees, the rivers, and the animals, but you miss the essence if you don't see the water cycle, the decay that feeds new growth, the interconnected web of life and death that makes the whole system thrive. The cosmos operates on a similar, albeit far more extreme, principle. A black hole is not merely a pit. It is a region of spacetime undergoing a specific transformation, a relentless ingestion. Its theoretical twin, the white hole, represents the opposite transformation, a violent expulsion. They are two expressions of the same underlying geometry, two sides of a single coin that the mathematics keeps handing us. The wormhole, or Einstein-Rosen Bridge, is the potential connection between these phases, the theoretical stem that links the root to the flower, and the Big Bang. In this holistic view, it becomes the ultimate white hole event, the moment our entire local spacetime geometry erupted from a prior state. This reframes everything. We are not floating in a static container dotted with strange objects. We are living within an evolving, dynamic geometry, a living structure that can bend, twist, pinch, and potentially rebound. Processes of ingestion and expulsion become the fundamental verbs of this cosmic grammar. A star collapses, spacetime ingests. A quantum bounce occurs, spacetime expels. This ecosystem view resolves the apparent paradox of the white hole's isolation. An animal that only consumes and never excretes cannot survive. It becomes a biological dead end. Similarly, a universe that only creates black holes, eternal sinks with no outlet, presents a profound informational and thermodynamic puzzle. The white hole, as a phase or a potential, offers an outlet. It suggests the cosmos has a way to balance its books, to process the extreme states it creates, and perhaps even to recycle them into new beginnings. This doesn't mean every black hole must become a white hole, any more than every seed must become a tree, but it means the potential is woven into the fabric of the rules. Seeing this interconnectedness changes the questions we ask. We stop asking, where is the white hole, and start asking, when does spacetime enter a white hole phase? Under what conditions does the geometry rebound? What does that transition look like, and what signature does it leave on the wider cosmic web? It encourages us to look for the ecology of spacetime, the relationships between the most violent events, searching for the hidden threads that weave them into a single, astonishing story of a universe that is not just expanding, but breathing, transforming, and possibly renewing itself in ways we are only beginning to imagine. The human mind is a relentless pattern seeker. We look at the scattered stars and connect them into constellations. We listen to the rustling leaves and hear a language. We search the chaos of existence for underlying order. This deep-seated need for symmetry and meaning is not a flaw. It is the engine of our greatest discoveries, and it is precisely why the white hole, a theoretical ghost in the cosmic machine, holds such an enduring, almost magnetic allure. It represents the ultimate what-if scenario, a direct challenge to the most basic intuitions we hold about reality itself. We are born into a world where things fall down, not up, where time flows forward in a relentless stream, and where creation seems to require immense effort, while destruction can be startlingly swift. The white hole confronts each of these assumptions. It suggests a place where gravity might, in a sense, push instead of pull, where the arrow of time could loop back on itself, and where the universe might create with a violent spontaneity that defies our linear logic. It dares us to imagine a cosmos that is not just stranger than we suppose, but stranger than we can suppose, yet one that still obeys a beautiful, hidden symmetry. This intellectual appeal goes beyond simple curiosity. It taps into a profound psychological drive for completeness. For every action, we instinctively seek an equal and opposite reaction. A black hole, a cosmic drain from which nothing returns, feels fundamentally incomplete. It leaves a narrative hanging, a story that ends in a silent, crushing period. The white hole offers the possibility of an ellipsis, a dramatic but then. It promises a resolution to the cosmic story, a way for the universe to balance its own books. Even if it remains forever theoretical, the idea provides a satisfying conceptual closure, a sense that the laws of physics might form a perfect, elegant circle rather than a set of one-way streets leading to dead ends. It embodies our hope that the universe is not arbitrary, but deeply, beautifully logical in ways we are still learning to see. Ultimately, the true power of the white hole mystery may not lie in whether we ever find one shining in the void. Its greatest gift is the journey of thought it forces upon us. The relentless pursuit of this mathematical phantom has been a crucible for our deepest theories. To even ask if a white hole can exist, we have had to push Einstein's general relativity to its breaking point, grapple with the bizarre rules of quantum mechanics, and invent entirely new frameworks like loop quantum gravity and holography. Each attempt to prove or disprove its possibility has cracked open new understandings of spacetime, information, and entropy. We have built analog universes in water tanks and super-cold atom clouds, and written simulations on the world's most powerful computers, all because this what-if question demanded new tools and new ways of seeing. In striving to comprehend the white hole, we have been compelled to comprehend the universe itself more deeply. The search has illuminated the edges of our knowledge, showing us precisely where our current maps of reality fade into blank spaces marked "Here be dragons." And in that illumination, we find not disappointment, but the thrilling outline of all we have yet to learn, a silent invitation to keep looking, keep questioning, and keep weaving new patterns into the endless story of the cosmos. Our journey ends not with an answer, but with a deeper appreciation for the question itself. We have traced the ghostly outline of white holes from a simple mathematical flip in Einstein's equations to their potential role as cosmic fountains, gateways, and even seeds for entire universes. We have wrestled with the paradoxes they create, from the flow of time to the preservation of information, and we have imagined the brilliant, fleeting signatures they might leave in the data of our most advanced observatories. This pursuit, spanning from the chalkboards of theorists to the supercomputers running simulations of digital universes, has illuminated far more than the fate of a single hypothetical object. It has cast a stark and revealing light on the very boundaries of our understanding, showing us where our most trusted theories of gravity and quantum mechanics strain and crack against the unknown. The white hole, in its elegant impossibility, has been a perfect tool for this exploration, a conceptual lever prying open the lid of cosmic mystery. It asks us to consider a reality where endings are transformations, where creation can erupt from collapse, and where the universe might balance its books across the chasm of a singularity. Whether these cosmic mirrors exist as physical objects or remain forever as mathematical phantoms, their value is undeniable. They have compelled us to build better detectors, conceive wilder simulations, and forge more complete theories. They remind us that the cosmos is under no obligation to conform to our intuition, and that the most profound truths often lie waiting in the symmetrical shadows of our equations. The story of white holes is ultimately a story about human curiosity, about our relentless drive to seek completeness in the cosmic narrative. So as we look up at the silent, starry expanse, the question lingers not as a frustration, but as an invitation. What other symmetries, what other hidden doors might be written into the fabric of reality, waiting for a curious mind to trace their outline? If this journey through cosmic possibilities sparked your imagination, consider supporting this channel by liking this video and subscribing for more deep dives into the universe's greatest mysteries. Let us know in the comments below, do you believe white holes are a real part of our cosmos, or are they the universe's most beautiful and persistent thought experiment?